Solid-liquid flows are inherently complex. Processes that involve more than one phase typically take considerably more effort to optimize than single-phase processes. Consequently, when planning an experimental test, whether on-site or in the laboratory, as shown in the figure, many variables and their interaction must be considered carefully. Instrumentation is far more restricted for multi-phase flows than their single-phase counterparts, requiring careful placement and analysis if successful results are to be obtained. Testing may be performed in dedicated laboratories or in the field. Both have advantages and disadvantages. Laboratory loops, like the one on the figure, offer controlled, highly instrumented setups where careful measurements can be made but may suffer from scaling issues. Conversely, on-site measurements allow flows of the actual slurry conditions to be monitored but must usually be confined to current production tolerances. The instrumentation is also often limited in both scope and accuracy. A typical instrumentation for laboratory tests can be seen on the displayed test loop. Key measurements include differential pressure, total flow rate, slurry density, and slurry temperature. More specialized measurements may include detailed concentration and velocity distributions within the flow. Installation of a transparent pipe section provides great insights into the flows and enables to identify the deposition limit velocity. Generally, any instrument that includes some form of prop that is immersed into the flow should be avoided in slurry pipe test. Continuous inline monitoring of slurry flow rate is most commonly accomplished using either a magnetic flow meter or Coriolis flow meter. Magnetic flow meters are non-intrusive. They operate on electromagnetic principles and rely on conductivity of slurry mixture. The magnetic flow meter should be installed in a vertical pipe if stratified flows are to be tested. The meters are relatively inexpensive and the most often used in both laboratory and field pipelines. Coriolis mass flow meters monitor the density of the substance in the pipe, the volumetric flow rate, and consequently, the mass flow rate through the pipe to a high degree of accuracy. They are not suitable for slurries that are strongly erosive or very coarse. Although now available for relatively large pipe sizes, the instrument and installation cost can become very high as the pipe size increases. Despite all of this, the ability to simultaneously measure the density and the flow rate provides an attractive alternative to other instrumentation. For laboratory pressure measurements, the best accuracy is usually obtained by using differential pressure transmitters connected with a pipe through tapping lines and setting pots, which prevent blockage of the tappings and protect the transmitters. The differential pressure transmitters are sufficiently accurate to measure the relatively small frictional pressure gradient while being insensitive to fluctuations in the overall static pressure. As for the flow rate, continuous inline monitoring of slurry density or solids concentration in the slurry is usually required. An inline density meter that monitors the in-situ density and hence the spatial concentration must be mounted on a vertical section of the line in established flow. A particularly useful device for measuring delivered density and concentration is a vertical inverted U-tube. The unit employs measurements of the pressure drops in the two vertical tubes of the U-loop using differential pressure transducers to determine the mean delivered concentration of solids. In measuring settling and complex slurry flows, especially for research purposes, detailed information about the distribution of slurry properties across the flow can be very useful. Local slurry density may be measured using a meter which relies on the attenuation of some form of radiation passed through the slurry. Gamma rays are most commonly used. The instrument measures local densities at different locations in a pipe cross-section and so detects a distribution of solids expressed as a concentration profile. Even more detailed information on the local distribution of solids can be obtained by tomographic techniques. Electrical resistance tomography, ERT, is by far the most common form of tomography used in laboratories, being relatively inexpensive, safe, and rapid. The technique involves sensing of local conductivity and its relation to the local solids concentration to get a concentration map of a pipe cross-section. The measuring units can provide almost real-time imaging, useful for operational control. As such, commercial ERT units are an attractive alternative to gamma ray density meters for slurry density measurements. By combining the output from 2 or more electrode rings, the map of slurry velocity can be also measured.